Okay, so we're going to talk about atomic structure and symbolism. This is the third domain of chemistry, right? Remember, the microscopic was the first domain, macroscopic is the second one. But we also have to think about symbolism, and this is going to be an important section. There's a lot here, and I'm going to go fast, so let's go. First of all, an atom, well, let's go back to these questions here. The proton contains the majority of the atom's mass, right? We'll say why in just a second. Protons and neutrons are much heavier than electrons, which we said that before. Electrons occupy almost all of an atom's volume. Say more about that in a second. The diameter of an atom is about 1 angstrom. Okay? The diameter of an atom is about 1 angstrom, and the diameter of a nucleus is 100,000 times smaller than that. All right? So let's put some character to that concept. So if you could take an atom and make it the size of a football stadium, then the nucleus would be about the size of a blueberry, right there in the middle. Okay, right there in the middle. I should make it blue, right? Let's make blue. There's a little blueberry. I don't know why it's so light blue. That's really a huge blueberry, right? But it would be an actual blueberry in there. A tiny blueberry in a football field is about the size of the nucleus of an atom, okay? So the nucleus is very small. Now let's talk about some units that we need here. A carbon atom weighs less than 2 times 10 to the minus 23rd grams. That's tiny, right? I mean, it's just so small, it's a very cumbersome number. And the charge of an electron is less than 2 times 10 negative 19 coulombs. Remember that from the previous conversation, 1 times 10 to the minus 19 coulombs, right? Well, that's a very cumbersome number. And this is a cumbersome number. So what we're going to do is we're going to use units called AMUs, where 1 AMU is that many grams, right? Now, in this case, the mass of a carbon-12 atom is 12 AMUs. Actually, this is exact because this is what the definition, AMUs come from the definition of a carbon-12 atom, okay? So nothing else is exact in chemistry, but a carbon-12 atom, just one atom, is exactly 12 AMUs, okay? So in the fundamental charge of the electron, 1.6 times 10 negative 19 coulombs, we're going to call simply E, right? So it's going to be plus 1 or minus 1. But that's what we're going to be talking about. It's the actual charge in coulombs is that, but we're going to call it plus 1 and minus 1. All right? So let's look at some subatomic particles now. The mass of a proton is almost 1 AMU. It's about 1 AMU, right? And its charge is plus 1 E. The mass of a neutron is also about 1 AMU, right? And its charge is 0. And the mass of an electron is about 1/20,000th. I can't tell. 1/2. I don't know. It's small, right? Can't do that in my head. 1/2000th. No, it's 1/2000th. It's 1/2000th of an AMU, right? And its charge is minus 1. You probably knew this from previous conversations, previous classes. All right. Now, the number of protons in the nucleus is its atomic number, and we're going to use the symbol Z for that. This is the defining trait of an element. If we change Z, we change the element, period. That's it. That's the definition, okay? For example, any atom that contains 6 protons is a carbon atom, okay? So if we take a nitrogen atom which has 5 protons and we give it a proton, it becomes a carbon atom. All right, so that's a nuclear reaction. All right, neutral atoms have the same number of protons and electrons, right? And so if you have a neutral atom, then its atomic number is the number of electrons, right? The mass number is the total number of protons plus neutrons. Mass number, which we oftentimes call A, some people use M for that, is protons plus neutrons. That's the mass number. This is going to pretty much approximate how massive a particle is. For example, carbon-12, the mass of carbon-12 is 12 AMU, right? Because it has 12 nuclear particles. And they each one weigh about 1 AMU. Now, the number of neutrons is therefore the difference between the mass number and the atomic number. We know that. So the atomic number is the number of protons. The mass number is the number of protons plus neutrons. And so you can get neutrons by taking those differences, right? You can get, this would assume that if I subtract P from both sides, I'm going to get N, right? N is equal to A minus P. That's what this down here says, right? Where P is, I'm using P and Z interchangeably, right? P is for protons, but Z is the atomic number, right? I probably should do that instead. All right. Now, ions are when you have a different number of electrons than the number of protons, right? And so the charge is the difference between the two, right? So if you have extra electrons, it's going to be negative, right? And if you have too few electrons, the charge on the ion is going to be positive. Cations, I guess we're starting with negative ones. Anions have a negative charge. Cations have a positive charge. We'll practice that a lot. You'll get a chance to show that that's easy for you, okay? Now, chemical symbols is an abbreviation that we use to indicate we have an element of an atom or an atom or the element itself, right? For example, the symbol for mercury is Hg, right? So here's Hg, that's mercury. Now, we don't differentiate because is that an atom or is it a bunch of atoms? And we're not saying Hg is simply the symbol for either an atom or for a bunch of atoms, right? That's nondescript. Some common elements in their symbols are as follows. These are in the periodic table. You know what? We're not going to talk much about this. These are things we'll see a lot this semester. Isotopes now, we have to indicate. If we're talking about isotopes, we've got to say with the symbol what isotope we're dealing with. The symbol for a specific isotope of any element is written by placing the mass number, it's a superscript, to the left of the symbol. So magnesium 24 looks like that. That means it's got 24 nuclear particles. Now magnesium all has 12 protons, so this must have 12 neutrons. 12 neutrons. Magnesium all has 12 protons, so this must have 13 neutrons. I'm not sure if I said that right. All magnesium atoms have 12 protons. Therefore, 25 must be due to the extra neutron, right? And the same here for this. Magnesium, it's got 12 protons, so it must have 14 neutrons, right? Because it's 26. All right, that's how we deal with that. Now here's more details on that. The atomic number, which we usually don't put because you know helium's atomic number is 2 because you looked at the periodic table, right? So this is sort of redundant. These two are redundant. But the mass number of a helium atom might be 4. Virtually all helium atoms have 2 neutrons, so that's legit to say. It would be 4. And it might, if it has a charge, the charge is going to be put right here. Not all heliums have charges, right? But not all helium atoms have charges, but in this one does because we indicate it with a +2. Not all magnesium atoms have charges, but this one does because we indicated it right here with a +2. Okay? Can you see here's magnesium 24? That means it must have 12 neutrons because all magnesium atoms have 12 protons, right? And this is the number of protons down here. You can see that these two are, that's redundant and say the same thing. All right, so we're going to be practicing with those also this semester. So here's in context examples of hydrogen. So hydrogen, we almost never call it protium. Hydrogen, all hydrogen atoms have 1 proton, right? There, look at that. Proton, proton, proton. Now, most of them have no neutrons. So if they have 0 neutrons, then that's going to be P + 0. Right? You know what? The author of this text is using Z for the number of protons, right? Z + 0, right? Well, this must be Z + 1, right? Because Z is 1, right? This must be Z + 1. So it looks like deuterium has 1 neutron, right? And here's one with a mass number of 3. Well, since it's hydrogen, it only has 1 proton because it's hydrogen, right? Therefore, it must have 2 neutrons. And this is this is very, very low prevalence in nature, right? So it's almost all hydrogen it's almost all of it, 99.989% of hydrogen has got 0 neutrons. Some of it, very small amount, has got 1 neutron, and even less than that's got 2. All right, but here's an example of how we build out that that symbolism with isotopes of hydrogen. All right, now the atomic mass, let's review this. Each proton and each neutron has a mass of about 1 AMU. Electrons weigh much less. So we say the atomic mass is approximately equal to its mass number. Since each of these has 1 AMU, we used magnesium earlier, magnesium 24, right? Magnesium 24 is going to be 12 protons plus 12 neutrons. Each of these weigh about 1. 12 times 1 plus 12 times 1 equals 12 plus 12 equals 24 AMUs, right? So magnesium 24 is going to be 24 AMUs. Now, not all magnesium is magnesium 24. So when you go to the periodic table, you'll see the average mass of magnesium is not 24. It's close, but it's not 24. Okay? And that's what I was saying right here. Most elements exist naturally as a mixture of 2 or more isotopes, right? And so the periodic table lists the average mass, all right? So we get the average mass. Let me come over here. We get the average mass by doing a weighted average, right? This is sort of series notation. This is just how you do a weighted average, right? So if boron, for example, is about 20% boron 10, there's 20% boron 10. So you take 0.2 times 10, it's about 10, right? And it's 80%, 11.8 times 11. I'm going to do my calculator. Put my calculator out here. Got it right here next to me. We're going to find that the average atomic mass is going to be, again, 20% of boron in nature, 20%, 19.9, 0.2 times 10 plus 0.8 times 11 is going to be 10.8. This gives me 10.8 AMU. Now, that was with my using round numbers. Well, I like to use round numbers, though, because I'm less likely to get lost. Now we'll go in and do the exact numbers that are given to us. It's really 19.9% of boron is 10.0129, right? And 80.1% of boron is 11.0093 AMUs, right? And that gives 10.81, which is pretty close to 10.8, right? I love estimating first because that way when I'm done, I'm confident I got it right. So anyway, that's how atomic mass is calculated. We'll be doing some of this in class, but it's important that you understand where those numbers come from and it's not scary to you when you see it. All right, let's move on.